This chapter, it's not like the hardest. I mean, there's new vocabulary for sure, but it's more, I don't know. It's not as it's interesting, but it's not as exciting as I think the next few chapters are going to be, because this is more like foundational. I don't want to say foundational. It's more of just like the nuts and bolts of it.
Yeah.
So
more coming later of the rest of the how it works. So I thought it was pretty straightforward. I mean, just the idea that we can get at the expressions that underlie our statements or our expressions. I guess we got the syntax tree, abstract syntax tree of them, which is pretty amazingly powerful. There's very few languages that let you do that in such an easy, straightforward way. In fact, the only one I can really think of is like Lisp, right? Lisp has this kid. I mean, there's a guy named Paul Graham that wrote a bunch of blog posts about this a while back. That his company was able to basically leverage the power of this writing code. I mean, it's funny when I was thinking about this morning or yesterday I was reading the chapter. I was thinking it was kind of funny, like why more languages don't let you do this, because when you think about it, this kind of meta programming. I mean, how many times are you writing a program and you're trying to figure out, you find yourself like repeating the same thing over and over again, or you're writing the same boilerplate over and over again because, you're like, how can I fix this so I'm not having I keep having to do these boring repetitive tasks. Wait a minute, that's something that computers are supposed to be good at. Why am I having to do it? Now, often you can use techniques, right, to capture that, into objects or into functions or something, but sometimes you need something like a macro, as they call my list, which actually is writing code. So I'm looking forward to seeing like how that works in R. Maybe there is other languages that let you do that, but it's hard for me to think of any at the moment.
yeah, I mean, like, this is the programming language that I use, and so it's neat. I mean, it goes underneath that underlying concept of like code is data, right? And if it's data, you should be able to capture it, inspect it, modify it however you want. So, I mean, there's a balance to that, though. It's not safe. It's not safe if you allow people to do that. So
but that's that's usually the case. Like list macros, for example, are extremely dangerous, and you have to be very careful what you do with them. C++ does have like meta template programming, they call it, which is also can be used to do fun and dangerous things, but it's not quite as flexible as just programming with the syntax trees, but it's pretty cool.
I guess that's another question that I had, and we could talk about it. Like, what does it mean by safe? Like, is it like the application of the language for a certain like purpose, or is it like, I guess,
I guess to my mind, I think of safety as being how easy it is to shoot yourself in the foot, like by accident, right? Just by not being super careful. But it's like anything else. If something's safe, you can be a little bit more relaxed about it. Like if you have a strong type system, you can be more relaxed. If something compiles, it's going to probably not, fail during runtime, that kind of thing, right? Whereas you have no type system, then you have no guarantees about that at all, and you pretty much have to test every possibility to make sure it doesn't fail, right?
That makes sense. And probably in certain applications, you for sure want things to be safe, like life critical things. You want to make sure that there's no like way that people can use the language in ways that will go against the logic of the program.
There is one other language that has this capability, sort of. It's C itself, with the C preprocessor. You can define these macros that can expand in all kinds of things, and that's known to be extremely very, very powerful way to shoot yourself in the foot, as they say. Sometimes it comes in handy, so you don't have to repeat yourself, right? That's always the problem, right? Don't repeat yourself.
Yeah.
I always think of like safety for no unintended consequences.
You're very low, Ryan.
Yeah, you're muffled there.
And muffled, like you sound like you're talking inside of a.
Sorry, how about now? Is that better?
There you go. Much better.
Oh yeah, way better.
I bet I had my hand over the. Yeah, I was just gonna say, like, it seems like when people talk about safety, it seems like they're talking about like unintended consequences. You know what I mean? Like, which is kind of what you're saying.
Yeah. Yeah. We always have unintended consequences, but if you can like reduce some of them, that's always better.
Yeah. Well, that was funny enough, I saw something, I don't know, somebody posted on somebody posted on Twitter, it was some stats professor somewhere, and he has like a whole like series of lectures, and I was just poking through them, and he brought up a quote from Hadley. Supposedly he wrote a paper about that, about like making statistics more safe so that more people other than statisticians can
Oh,
do
I like
this
to see
kind of
that
stuff.
paper. Yeah.
Yeah, I could dig it up. Like I said, I was just like I just was like wondering, oh, I wonder what this person has. And then I just was like digging through like one of their lectures, and I was like, oh, I didn't even know Hadley had a paper about that. But yeah, it's like the idea of like trying to make functions that are safe so that people can fall into that like pit of success, right? So it's
Yeah.
not like, so you don't need to have a statistician to necessarily do everything that you possibly need, because they're safe functions or safe libraries. And so
Oh,
yeah,
I
probably
just was looking, I was Googling in the side here, what other languages might have macro capabilities, and it turns out that Rust has a extensive macro capability for metaprogramming, which is kind of cool. So a newer language like that.
yeah, that's kind of cool. There's some discussions about Rust. So not in this, but some interesting stuff about Rust in itself, but I just don't have enough hours in the day to
Oh.
even try and take it on.
And another new language that has Julia, which also has a lot of roots in Lisp. So I'm not too surprised that it has similar things like R does, where you can get at the parser, you get at the symbolic tree.
Oh, that's cool. Yeah, Julia is another language that
It's on my list, man.
it's interesting.
Yeah.
I don't, yeah, I think Python's probably next for me, but all interesting. So I guess we'll probably get started, kind of walking through this stuff.
Just a fun discussion to have, because I think about these things all the time. Like, what kind of capabilities? Why don't we have more languages have these kinds of capabilities? That drives me crazy. But
I guess I also wonder if that's an issue too, of why, and this is actually a good conversation. And like, if we don't get through all this stuff, that's fine, because most of the stuff is pretty straightforward. But I think like, I wonder if there's that conversation of why more productionized systems rely on Python. Not saying that you can't productionize R code, because there are organizations that do that, but Python's more safe. I don't know if that's true or not. Would that be a fair statement to say? Is it more safe than like, does it allow you to do like this meta programming stuff? Or
I think it's also a speed issue too, right? Isn't like Python's a lot faster. So I mean, that's another kind of safety issue is,
I wouldn't say it's intrinsically more safe. I would say that just because it's been used in production for so long, that a lot of the gotchas have been solved, right? I mean, it's used in production everywhere, right? I mean, a lot of websites now run on Python, to Django, and all those systems are being used. So,
no, I don't know. Just a thought, just why there's comparison, especially like.
I think R will get there. Although I do see this kind of interesting synergy of Posit and Python too. So maybe meet in the middle somewhere. I mean, if you can like use R for your statistical stuff and then easily flow into Python for your production stuff, that'd be ideal. I think they're kind of getting there on that with articulating all that.
Well, I mean, like you now can do R code with WebAssembly, I think. So you can run, if I know the technology correctly, you can run R native in the browser with WebAssembly. So it's definitely going to increase in like application for sure. But like you said, just Python's used everywhere, not just statistics or data science or anything like that. It's everywhere.
Right. Yeah,
so.
That's what I'm saying. So it's had a lot more trial by fire, or however you want to say. It's been, what's the word? Tempered by the fires of extensive deployment.
Yeah. So, excellent. So I guess we'll probably just get started here. Let me see if I can share my screen. Share so everybody can see my notes. Everybody see my notes so far?
Yep.
Yes.
All right, cool. All right, so like we've just been kind of introducing tonight, what we're going to do is we're going to talk about expressions. And really, I think these are the things that we need to get out of this. Really, I think we just need to kind of understand the idea of the abstract syntax tree, or the AST. Also discuss some of the common data structures that are going to underlie the AST. That includes constant symbols and calls. There is a fourth one called pair list, but as you'll see later on in the book, it's like Pair lists are pretty much replaced now by lists, so we won't cover that too much. Then we'll kind of explore the idea behind parsing, explore some of the details of R's grammar, and then kind of dive into some examples of using recursive functions to compute on the language, which I kind of understood the examples, but maybe if we could talk a little bit more about them to better understand them, I think that would help. And then we'll work with 3 more specialized data structures like pair lists, missing arguments, and expression vectors. And so obviously we're going to use 2 libraries in here, rlang. Rlang is going to help us do some of the metaprogramming stuff that we want to do. And then lobster, however you want to pronounce it, will be used to kind of do some inspection of our expressions. And it gives us the function AST to actually create the abstract syntax tree. So I thought this was a really interesting quote. And I think this is really important. It's just the idea that to compute on the language, we first have to understand its structure. So it goes back to last week when we were talking about the big picture, this idea that code is data. Thus, if it is data, we should be able to capture it, inspect it, and modify it for our purposes. But for us to do that effectively and to compute on the language like that, we need to understand its structure. And so a lot of this chapter is kind of like setting the foundation of what do we mean by expression? What are the elements of an expression? What's the behavior of these expressions, so on and so forth. So if we're going to understand the structure, we need some new vocabulary. We need some new tools to inspect and modify expressions. And we need to approach the use of the language with new ways of thinking. And so it really starts off with this one example here that thinking about that we need to make this distinction between the operation and its result of an expression. And in this case, the book talks about that if we try to run this in our console or we try and run this in R itself, we're going to get an error, mainly because there is no value of X. But what we can do is we can transfer this into an expression so that we can capture the intent of the code without executing it. And so once we capture it and capture that intent, we can evaluate it, we can modify it, we can change it however we want with that, but we have to do that using something called an expression. Expression, to create it, all we need to use is this rlang function called expression. All it does is it just captures the intent of the code without evaluating it. So in this case right here, I'm just assigning this expression to this, I'm assigning Z to this expression here. And then if you try and print it, you'll get this expression printout right there. Now, if we want to evaluate it, like we talked about last week, we need to use this base function called eval, and then the expression that we want to evaluate, and it will evaluate. And we talked about last week that evaluation requires 2 things. It requires an expression, it requires an environment. And in this case, because we're not passing an environment, it's going to look into the global environment. Thus, that's why when we run Y after evaluation, it becomes 40. So pretty straightforward. Then the book kind of talks about this idea of, well, you can have multiple expressions. You don't have to have just a single expression. And so some of these notes were from the last cohort. So some of this part I really didn't understand why they had it in there, but it's basically the same idea where if you wanted to have multiple expressions, all you have to do is just pair them together with, with a comma inside of expression, and then you'll have 2 of them. Now, if you want to evaluate it, and again, this comes from the previous, cohort, and I really didn't understand why they had this for loop example in here. But basically, I think it was to evaluate both of these expressions is I think what they were trying to do, but I didn't know if that was the case, if you needed to do this every time if you had multiple expressions. I think you do, but yeah, this one wasn't in the book and I didn't really know where it came from, but just kind of a heads up that if you do have multiple expressions and you want to see both of them printed, you'll have to do like a for loop.
Do they like import the whole R expression namespace? So I can't, some of these things are based on some are R expression, right? I'm confused, I guess, about that.
Yeah, that's where I got kind of mixed up too, because rlang provides expression, which is which captures the expression of it. And then I think there's a base expression, and eval is base too. So what I assume is that if you're going to have if you're going to have multiple expressions, I wonder if our-lang expression doesn't take multiple expressions. And so if you did want to do this, you'd have to revert to using the base expression and then eval. But if you wanted to print out both of these expressions, you would have to do like a for loop to see them. That's what I'm guessing. But the book really didn't talk about this too much.
Just vaguely remember something in the book about there being about these list of expressions that the R expression did have a way of handling it, but I can't remember what it was now. Or R-lang had a way to deal with it, but I can't remember what it was now.
I think that might be towards the end of the chapter. I think there's something about it, like especially within the example. I'll have to look at it here in a second. I'm not 100% sure. But basically, just right now, I guess the big things to take away from this is this idea of if we want to capture the intent and the structure of our code, we need to use R-lang expression. And then if we want to evaluate it, use base eval. And then if you want to do multiple expressions, you have to use the base expression and then the base eval together. So for me, I don't necessarily foresee me using this, but it's available if you need it. So
Right.
So the next kind of component about this is this idea of the abstract syntax tree, or the AST. And when we think about this, expressions are objects that capture the structure of our code without evaluating it. That's all an expression is. So basically, that's the one thing that you have to remember about expressions is it's capturing the structure of the code without evaluating. The other thing about expressions is it's not just character strings. Expressions can be expressed in an abstract syntax tree. And because the structure of the code is hierarchical, it can be naturally represented in a tree-like data structure. And so it's really important for us to understand this tree-like structure because it allows us, if we can understand what that tree-like structure is, it allows us to more effectively inspect how the code is going to be evaluated, while also being able to modify specific components of that abstract syntax tree. And so when you think about this, the branches of the tree are going to be your calls, and calls in our case here are going to be functions, and leaves are symbols, in other words, names of objects, and constants. So to give an example here, we have this function f, which has these arguments x, y, 1. And so in the handwritten version, here is the symbol f because the function's name is f. And then we have this symbol x, which is this argument here. We have this constant string y and this constant 1. Another way to represent this is to use the lobstar AST, which will print it out into your console. Again, it's going to be in a hierarchical structure. Branches are going to be these darker rectangles, which are going to represent calls or functions. And then we have our symbols and our constants like this. Okay. Now with the AST, we know, or with the language, we know that we can nest our function calls. And so here's a more kind of complex nested function call where we have this function I, we have this function H, G, and F, and we have all of this nesting. I is nested with an H is nested with an F, while G is also nested with an F. This kind of complex call to all these different functions can still be represented into an abstract syntax tree. It's just now you have a deeper hierarchy because of the nested calls. And so you can see now here's our I symbol for that I function. And then here's our H function with the constants 3 and 4, our G symbol for 1 and 2, and then F. And correct me if I'm wrong, but the way I kind of read this is if I'm looking at like this abstract syntax tree, I start from the bottom and work my way up. Would that be a fair statement? Because like when I look at this, when I'm first like looking at the nesting, I would say, okay, the first function that gets run is I, and then H with 3, 4, and then G, and then F. So I usually read these starting from like the bottom, the deepest depth, working my way up. But I don't know, did anybody else have any other interpretation of how you should interpret that?
I hadn't put it in those words, but I think that's a solid strategy.
Yeah, I agree.
Because I think of it like this is the root, right? And it's probably not the best way because it's talking about branches and trees, but like work your way into the root of it. So that's the way I've just been kind of thinking of it. But again, it can be represented not just hand drawn, but using AST. Here it is. And again, because it's so nested, it starts at the bottom. And so the previous cohort kind of left these kind of like rules of thumb. Like if you're reading hand-drawn diagrams, they say read it from left to right, ignoring vertical position. I don't necessarily know if that's, you can read it that way, but I think if you want to know how it runs, you should read it from bottom to top. But then with the lobster drawn diagrams, you go from top to bottom, ignoring like horizontal position. But then you also need to consider the depth, because your depth is going to be determined by the nesting of your function calls. So, and then the other important thing about nesting is that the nesting is going to determine the evaluation order. And we'll talk a little bit more about that when we get to parsing and grammar, because there are some rules that go with this, especially with operator precedence, where function calls or calls get put within the AST. And so that's going to be something that we're going to talk about a little bit later. The other thing that's important to remember, because of lazy evaluation, this AST is not always guaranteed. So because remember, if you have a function call that has an argument that is not computed within the function, that should not be represented in your AST until that function computes using that argument within the function. So something to keep in mind, because lazy evaluation also affects how the AST is represented. Okay, any questions about like the basics of the abstract syntax tree and how we use that to represent like function calls, symbols, and constants? Okay, cool. So, okay, cool. Well, we're going to take it back here a little bit with the idea of infix calls. So really kind of going back to that kind of foundational concept when we were talking about functions, this idea of prefix functions or prefix form and infix form. And it's really kind of cool to see how this comes back when it comes to looking at the structure of the language. This idea is that every call in R can be written in tree form, because any call can be written in prefix form. So here we have this infix form here where we're doing just a multiplication. So we're taking this object X, multiplying it by 10 and assigning it to this value Y. This is the infix form. If we wanted to put this into prefix form, we could do it like thus right here. And what's nice about this is, regardless if we're in infix or prefix form, because they are the same and they evaluate the same, you can represent these in an abstract or in a similar or an equivalent abstract syntax tree. And so that's what basically this is what it's showing here. So if you run an AST on either of these kind of expressions, you should get the same abstract syntax tree. So obviously we have the assignment symbol, and I had a question about this, but we have the Y symbol, multiplication symbol, symbol X, and then a constant 10. So I had a question about this right here, about the assignment operator. Is this considered a symbol because that's the name of the function? Or the arrow, excuse me. Is the arrow known as a symbol because that's the name of it? Okay.
Yeah, it's a symbol.
Yeah, it's just it's a function, just like anything else. I think, right?
Yeah, so it's a function, but it's not technically a call. Is it a call? That's what I'm wondering, because the name of that function is this. Is it a call too?
Yeah, it's a call.
Okay.
Yeah. I mean, that structure represents a call, right? There's a symbol in the first position, then the arguments are after it, right? Or not the argument, but yeah, the arguments. Yeah, sorry.
Oh, okay. Okay, okay. Because that was what was confusing to me when I was sitting there thinking about this, because a lot of things can have, or you have to name things and you have to name functions. And this is technically a function. A function is a call, but the name of the function is a symbol.
Yes.
The symbol being the arrow.
Yeah, the name of everything is a symbol, right?
Because everything has to have a name.
Well, not the constants, right? So 10 doesn't have a name, but
Mm,
the black boxes are constants, and the other things are symbols, basically on the leaves.
that makes sense. Okay. Anything, okay, yeah, that makes sense. So constants don't necessarily have names, but calls can have names.
Yeah.
Okay.
I
Okay.
mean, you can have an anonymous call, right? You could have, and it shows later, he shows where you have like a function, anonymous function in there instead of a symbol at that first position. So you have like a more interesting tree. That's later in the book, but I'll try to point it out when you get there. It's say, here's the case where the function is not a symbol, but in this case, the symbol points to a function, essentially, or refers to a function indirectly.
Okay.
Remember, you have
Okay.
anonymous functions. They don't necessarily have to have a name. So
That is true. That is true. I forgot about anonymous functions. Okay. Okay, so then basically here's just the AST for the same expression that we have here. Obviously, it shows the same kind of operation. And then if we do this in the prefix form, the AST is still going to print it out the same because they are equivalent. They are the same thing. There's no difference between these. So they're just going to, so there's no difference between these ASTs. And if you generate an expression with a prefix call, so say you want to create an expression, but you want to define it using the prefix form, once you create that expression, it's going to print it out into the infix form. So just keep that in mind, that if you are creating expressions like this, it's still going to output that expression in that infix form. So just you should know this kind of thing. So the book kind of goes a little bit further into diving into the specifics of these expression components. So big thing to remember is that collectively, the data structures that we're going to talk about in the AST are expressions, right? They're just a collection of these different elements together to create an AST, which is an expression. And so these include things like constants, symbols, calls, and pair lists. We won't talk about too much about pair lists until we get to the end, but really the ones that we should know are constants, symbols, and calls, which we've already talked about a little bit here. Constants, they're just scalar constants. They're the simplest component. These include null or length one atomic vectors. So things like true, a 1L integer, a double 2.5, or this value x. If we want to test for a constant, we can use this is syntactic literal function from R and Lang. And then the other kind of big kind of characteristic of a constant that we need to know is they're self-quoting. So even if you create an expression using these, they are identical to the same constant. So if you did expression true and compared it to the true scalar constant, it would be the same. So identical just tests for equivalency, it returns true. Same thing for a 1, double. These things are true because an expression is the same. So they're known as self-quoting. Same thing with an integer, same thing with a length 1 string value, so on and so forth. So pretty straightforward with a constant. Symbols, they represent the name of an object. So like if if you had a name X or a data set MT cars or a function named mean. Now, the book kind of has this argument of that symbol and name can be used interchangeably or can be interchanged with one another. But the problem is that name has a lot of different meanings to it in the language. So it's better just to call it a symbol. So a symbol representing the name of an object. However, you can both use is.name and is.symbol to check if you have a symbol. You can create a symbol in two ways. You can either capture it, using expression, or you can turn a string into a symbol using the R-lang sim. And so these are what these examples show you. Expression X returns this expression X, or this R-lang symbol with the string X, you return X. You can test these, or you can reconvert these into character by doing as.character or the R-lang as_string. The book says that if you are going to convert this expression back into a string, it's best to be using R-lang as_string so that you're being explicit and you're signaling to people to say like, I am explicitly turning this into a string. So you can recognize it because it's printed without quotes. So if you want to print this, if you print the expression out, obviously it doesn't have the quotations around it. So that should be a tip to you that it's a symbol. If you call a structure or stir on it, it will say symbol X. If you want to test it, is that symbol will return true. The other thing the book talks about is symbols are not vectorized because symbols will always be a length 1. So just keep that in mind that they are not vectorized. But if you want to use multiple symbols, you can put them into a list and then use this function rlang sims, and then you have a collection of symbols or a list of symbols that you can use in your expressions or whatever you need to do. Pretty straightforward. I don't think there's too much of a surprise there. Calls just represent functions. Call objects are like lists. So that basically means that we can use standard subsetting operators to subset calls. So the first part of that object is going to be the function name symbol. The rest of it is going to be the arguments. And then it's important to remember that calls create those branches within our AST, and then the nesting of our calls is going to determine the depth of the tree. So you can identify the call object when printed because it looks like a function call, and just be aware that using type of and string is going to print this, this language object. It's going to call it language. So if you really want to test if you have a call object, it's best to use this is.call, which will return either true or false. So here's this example with the AST. We obviously have this call here, read.table. And then basically what it does is we have the call read.table, and then we have the first part of it, which is the string important.csv, and then this argument row.names. Now, this is where I had a question going back into the AST. What is false in this case? Because this is is this whole thing a symbol, or is rows.names just a symbol?
That's a good question. Yeah, what is going on with that? He did say something about it. I didn't quite grok it. Translation, I didn't get it at all.
Because technically this would be
it's like this reason why you should, it's related, I think, to the equal sign is treated like there's 2 different equal signs in advanced R. He mentions that somewhere. There's the equal sign you use instead of an arrow, like a first assignment, then there's equal signs for optional arguments, or for arguments like this.
Yeah, this one I don't know, because this is like, I know
like, why didn't that expand to a second tree, right? Like a equals is a root or something, but it doesn't. If you have an assignment, it will.
Yeah, that's what, because false would technically be a constant, right? Like false would be a constant, unless this is 2 things. This is a symbol, which is the argument.
Yeah, what section of the book is that where he talks about that on the calls?
18, no, not 18.7.
That's 18.33. I think. Yeah, I got 18.33. Yeah, I remember looking at it. What? So what kind of thing is that? Is what you're wondering. I wonder too.
That I'm not sure, like, because you can subset it out, right? Like that's what's coming up next, is the idea of like, okay, if you want to subset these items out, you can, where you could pull out like the element row, what is row.names using the $sign operator, which we just talked about now when we get there, and it returns false, right? So like this is the case right here, because these calls act like lists, we can subset them, it would return false.
Oh, yeah, that's right. So to get those elements, so I guess it's a different kind of structure in the symbol tree, right? It's actually true is the constant, but instead of being indexed by position, it's indexed by row names. So you have to use that $sign row name to get that part of the tree. You can't, I guess, what can you say? I guess I should try copying.
Well, unless because it's still representing.
Yeah, interesting.
Like branches are still either a constant or they're a symbol. It's just this is like a symbol constant, right? Like
Yeah,
it's
no,
row
the constant is
names.
false, but instead of being number 2 in the abstract symbol trees, is row names part of this abstract symbol tree. It's a named part of the list, right?
Mhm.
It's funny they did it that way though. But
And maybe that's the only way you could capture it. I mean, so that's the question I had. I don't know if anybody can answer
yeah,
that one,
I
but
don't.
that one I don't know.
Yeah,
So
interesting.
So to continue on, basically, we were already talking about this, but calls are just like lists. So they behave like lists. So because they are list-like, we could just use the standard subsetting operators. So here, if we go back and we want to take this object X and then subset out the first element of the call, it's going to be that symbol read.table. We can test that with this .symbol. It is true, so it is a symbol. The remainder of the elements are just going to be arguments. So, but this is where gets confusing right here. See, we have as.list. We're going to subset it out. We have the first argument, which is important.csv, but now we have this row names false. Shouldn't this first? Go ahead.
You can ask for like the I did check that out. You can also get that false thing by asking for like what do you call it? AS?
AST, the lobster function.
No, the expression he's calling it AS. Is that what he's calling it? In the right as the part you were in already. When he anyway, if you call our laying expression on that thing, right? Instead of like he did below X, he calls it X. Okay, fine. He calls it X. So X sub 1 is going to be important. Is going to be read table, right? X sub 2 is going to be important CSV. X sub 3 is going to be false. We can also get that by doing X $ row names. I just did this in R, so that's why I was curious about that. So it's got a name. In other words, that expression has names. It has a names attribute, and the names attribute has 2 blanks and then row.names. So row.names is really just the name of that third component of the abstract symbol tree.
Okay.
It's just a regular vector, right? Well, it's not a regular vector, but it acts like a vector like that, right?
Okay.
I mean,
That's
it's type of language, but if you
okay. And I might just be getting hung up on it. I mean, you still
I was
understand
getting hung up on it too. I see what you're saying, but yeah, it's just the third thing is called false, but it's also got a name. It's also got a name, row net names, which is important to when you evaluate it because it needs to know that name. But
well, here's the other thing too, though. Like,
so that equals means a different thing there. It's not an operator there. It's just part of the syntax of assigning a name to an argument.
Okay, but here's the other thing too, is like
Or
with this, because like if you look at this function here, right? So read.table, this is the first argument. Well, this is the first value of the first argument, right, of this function.
Yeah.
But then when you try and subset it, it doesn't return a name because there is no name for it. Where is it? I'm getting lost here. See, so if you subset it, important.csv doesn't have a name associated.
Right, it has no name, right? And if you look at the names, if you call names on it, you will see that, or if you look at call names on X, you'll see that there's the first thing doesn't have a name, the second thing doesn't have a name, but the third thing does have a name, and that name is row.names.
Interesting.
In RStudio. Play with it in RStudio. I think it helps make more sense out of it. But
okay. Well, anyways, it goes back to the fact that you can subset it.
Yeah.
So
no, I'm glad you brought that because I kind of glazed through that, like I don't really get that, but maybe it'll make sense someday. But so you're questioning it, maybe dig a little deeper.
Yeah, it might be something that we need to dig. I mean, it could just be because they can't, represent it in the AST, so it's just going to treat it as its own branch because it's an argument. So okay, cool. You can determine how many arguments are there by just, taking length of X, subtracting it by 1. If you wanted to do that, you can do that to kind of figure out how many number of arguments are in there. The other thing to remember too, is it's really challenging to extract specific arguments, mainly because of how R does argument matching. Because remember, argument matching can happen either by location, by its full name, or its abbreviated name, or with no name. And so there's just really flexible rules. So if you're going to use this type of subsetting to pull out a very specific element, it's going to be really, really hard because there's several matching rules that you're playing with. So if you wanted to do this, the book suggests using call standardize, because what it will do is this call standardize will make sure that it's using the full argument names. However, this doesn't work in all cases because the triple dot or the 3 dot, if your function uses that, it's not possible to standardize all of the arguments if your function uses a triple dot. And then just like because we can do subsetting, we can also modify just like we would normally do with list elements. We just say which one we want to modify, here in our case, header. If we wanted to add an argument header to this expression, we would just use the $ header and then apply this value true to it, or assign this value true to it. We'll print it out. Here you go. New arguments added to it, header true. So function position. So it's basically, again, the first element of the call object is going to be the function. You know, this contains the function that will be called when the object is evaluated and is usually a symbol. So here we have this function foo. If we do the AST on it, we're going to get a branch, which is foo. Pretty straightforward. This also remains even if you quote your function call or quote the symbol for the function, the AST is still going to output this branch foo. Really important is that sometimes the function doesn't exist in the current environment. So sometimes there has to be additional computation to retrieve it. So some examples might be if you're trying to find a function in a package, if you're trying to find a method within an R6 object, or something is being created by a function factory, the AST may need to use other functions before or to capture the structure of your code. So here's this example of this function foo, which is in this package PKG. And so what it has to do is it has to use this call, the double colon, first to say, hey, find this function foo in package, and then run the one inside of foo. So you may need to do some extra computation. And if that function is not available in your global environment, it may have to do some looking in some other areas. Same thing with this. We talked about R6. This could be a method foo in this object or this class object. Same thing. It has to use this additional computation to find object or this method foo in class object, and then it can produce the one. So. And then here's just like the ASTs of what this looks like. And then here's just the handwritten ones for all of them, but I don't think we need to spend more time looking at these than just seeing them. So any questions about this extra computation that may need to happen in the case of like packages or R6 methods? No. What I found interesting is that this is a call, like the double colon is a call. So that was kind of neat to better understand, but
yeah, I thought
Okay.
it was like a special scoping operator because it looks like a scoping operator from like C++. I didn't realize it was a just a call.
And what's interesting, so I was looking at this because you can look at the syntax. So I was looking because the book talks about like if you want to see like the precedence, the operator precedence. It's interesting to see that double colon or triple colon is like up there in precedence.
Yeah.
So I thought that was kind of neat.
It's the highest, right?
Yeah, it looks like it's one of the highest, at least the way I'm understanding this. But yeah, it's like one of the top. So, which makes sense, right? Like if you're trying to find a function that's defined not in the global environment, but inside of a package, you know, that should take precedence over other operators. So. Constructing. So you can construct expressions. You're going to use this function called call2 from rlang. It's just basically using the same conventions that we were doing. So the first argument of call2 is the name of the function you want to call. This could be either a string, a symbol, or another call. And then the remaining stuff that you pass into it is going to be arguments. Now, big thing to remember is if you are going to have, if you want to define like if you want to capture the structure of an argument, but you don't have it defined, you have to use expression to capture
Right.
that as an expression, or else it's not going to work. So same thing here. Here, this is a symbol, or no, this is because this is a string, mean. This is a symbol because we're doing base mean, because we're using the mean name to pull the function from base. And then,
Right, they'll just keep it unevaluated. I guess you didn't have the expression there, you'd end up with the actual function itself in there, right?
or would it, yeah, you would just have the function name. It wouldn't be like it wouldn't be the function definition as an expression. It would be the actual function.
Yeah.
And in that case, would it just print?
No, let me see. I'm
Because
curious.
because if you do base, I think it'll just print like. So if we do like, if you do base mean, yeah, it would just, well, because it's an S3, it's going to use method mean, so it would just print.
Yeah, I did it. You get the function X use method mean thing.
Yeah.
In there instead of base mean. Interesting.
So if you want to capture, oh, go ahead, Ron.
It's kind of interesting, yeah. So you need, if you're right, so you need to make sure you put, I guess you'll know when you do it, you forgot to put the expression on there.
And that's what I think a lot of these R-lang functions are doing, is it's like, this is a pattern that you're going to be doing in metaprogramming. So it's probably a safe way to metaprogram, or it has some like guardrails to make sure that you are metaprogramming correctly, I guess is the way I'm thinking of it. I don't know R-lang as well as I probably should, but it's very clear that if you want to do metaprogramming, you probably should know a little bit of R-lang, because it seems like it tries to abstract some of those patterns out for you. So infix calls are the same. So if you want to do it rather in infix rather than prefix form, you can do it this way. And then obviously the expression gets outputted like that. So parsing and grammar. So parsing, this is the process by which the computer language takes a string and constructs an expression. So the other important part about parsing is that parsing is governed by a set of rules known as a grammar. And so what's really nice about using Lobstar AST is it gives us the ability to look at the details of R's grammar. So what are the rules that it follows to parse out the characters that you're writing in to represent whatever you want to do, or whatever computation you want to do. So the first thing that comes up with this idea is, with these ideas of looking at grammar, is operator precedence. So there are certain conventions used by programming languages to resolve ambiguity. And so we talked about this a little bit last week, but there is, when it comes to infix functions, there becomes two sources of ambiguity. So the first one comes with like which operator gets evaluated first. And so, you know, the example in the book is this idea of 1 + 2 × 3, right? Do we get 9, which is 1 + 2 × 3, or do we get 7, which is 2 × 3 + 1? Now, if you're using PEMDAS, parentheses, explanation, explanation, so on and so forth, you would get 7 rather than 9. But R, because there's ambiguity in how it evaluates and parses the code, it has to have that grammar rule set up that PEMDAS is used. And that's what basically is happening here, is that you can view the AST, and the AST will represent how this is supposed to run. So if we ran AST on 1 + 2 × 3, we would see that it does follow PEMDAS. It would do multiplication first and then addition, to which would evaluate to 7. So now that's a pretty straightforward run, because, you know, PEMDAS is hammered into us ever since we learned basic math in school. But there are other places where certain operators aren't necessarily as clear. And the one that is surprising, the book talks about, is the exclamation point. which is kind of interesting because I was just, when I showed that earlier, the syntax, you can see that the explanation point is way down in the level of precedence. So, I mean, there's other ones that get lower precedence than it does, but it's pretty far down there in comparison
Right.
to others.
As long as it's higher than the and or, it shouldn't cause any problems, but
Yep.
it's clearly less than the infix operator.
Yep.
Interesting.
So what's really cool about this is, because I don't know how many people have done this before, but I've used this quite a bit, is that, like, say you're trying to do this like X in Y, which is just trying to find matches. You can flip this to be the opposite if you write like the exclamation point first. But in the AST, this makes a lot more sense. X with this operator, this infix operator in, Y gets evaluated first, and then it negates itself. So then it flips the expression. So
We'll always put parentheses around that because I didn't realize it. There'll be lower precedence.
yeah. The book really says, like, hey, there's like 30 infix operators divided into 18 precedence groups. So, I mean, if you really want to study them and memorize them, you sure can. But the book is like,
Pass.
nobody really does. Just pass.
Yeah.
So if there's any confusion, just use parentheses, right? So if for some reason we need to override, PEMDAS, you can put parentheses and we can get 9 to evaluate rather than this. But just, if you want a certain ordering, use parentheses. It's pretty straightforward with what I was talking about. But it's just really important to kind of know, because that's a form of ambiguity, right? Like, certain operators get precedence over others. And so if you want to know the structure of the language, you need to know which operators gets precedence over others. So, and if you have questions of that, type in question mark syntax and you'll get the full explanation of what goes where. So, okay, where are we at? Well, we got about 7 minutes left. I for sure will not get through all of this, so we'll probably have to take some next week as well. Another form of ambiguity is associativity. This one, it really comes into what happens in cases where you have repeated usage of the same infix function. So in our case here, the infix function of addition is used twice. Now, it doesn't really matter here, because regardless if you do 2 + 3 + 1 or 1 + 2 + 3, we'll always evaluate to 6. However, if you wanted to force this, obviously use parentheses to get whatever operation you want to do first. But in this case, it doesn't matter, but in other places, this might matter. So the example in the book was this idea of ggplot2. So if people are familiar with ggplot2, which most people are, is every time you use ggplot2, what you're doing is you're creating layers, right? You have to start with ggplot, do a plus to add another layer to the plot. Then you use plus to add another layer. But the problem is if you don't do it in a certain ordering, then your plot is not going to render correctly. And so it really matters in cases like this, because the plus, and the book says it's over, can't remember the exact terms that it used, but it's like, it's over, I can look them up, but it's like it's overused. And so it has to make sure that there are certain rules to dictate how those things are actually being expressed and used. And so in our case here, with the 1 + 2 + 3, we can see that 1 + 2 goes first, and then the 1 + 2 and then +3. And the book really mentions that R is left associative. So the operations evaluate from left to right, if I'm correct, if I'm saying that right.
I think so.
Okay. There's 2 exceptions to this rule. So every rule has an exception. So this is not the case for exponentiation or assignment. Right. So obviously, when we look at PEMDAS, parentheses, exponentiation takes precedence over, multiplication, division, so on and so forth. But that's what happens here. So
But this
we
is not
would-
this is not a precedence issue, it's an association issue, right? There's two.
Association, you're right,
Yeah.
you're right, yep.
So the association, they're right associative, because that's just the way we're used to it, I guess, from a mathematical perspective, but. Right,
Good catch, I definitely.
2 to 3.
Yep, good catch. I definitely said that wrong. So, so then you'd have the 2 raised to the power of 3, and then the result of that 2 to the raised to the power of whatever this was. So,
Yeah.
and the other exception is assignment. So assignment is going to be right associative now.
Yep. Right.
Okay.
Associative, yeah.
Yep, because it's going to start with the value of z, move over to y, and then x. And so then here's the abstract syntax tree for it. Shows you z, y, x, so on and so forth. So
You know, that-
exceptions to the rule.
I'm gonna
Go
put
ahead,
that
Ron.
lobster AST in my toolkit though, just occasionally check out like, oh, wait, do I need, which way does this get evaluated? Okay, now I can see, kind of nice, right?
Yeah.
Real quick.
Especially if you have like really nested stuff, like
Yeah.
it would be nice to like, and you really shouldn't be I mean, like there's a point where if you nest things too much, the readability is,
Yes, yeah.
it's beyond what you should do. But like, if you had that situation, you could, get a better view of it and see what's actually happening. So, where am I at?
Yeah, it looks like still got quite a bit to do. Like, how do you want to deal with it? Do you think you can finish it quickly, or do you want to just take the whole session and wrap it up properly, or do you want us to read and prepare the quasi quotation, or?
I think quasi quotation is going to take multiple too, don't you
I
think?
know, I do too.
Yes. Well, I really I think I could probably take half of next time.
Okay.
Because really these examples, I mean, I don't know how much y'all want to dig into like these examples, because yeah, I mean, we could dig into them, but they were kind of, I don't know. Yeah, I probably could get this done, because really pairless, missing arguments, expressions, that's not going to take very much, because pairless are outdated. Missing arguments, there's maybe 1 or 2 points, and then expression vectors, the conclusion of that is just use lists. So
Yeah.
really the only thing we have left is like parsing and deparsing, and then talk about these 2
Right.
examples that are really going to take most of the time. So probably half the time. So I would probably just say, see how far you can get with the quasi quotation.
Okay.
If you're good, I mean, if you need more time, we absolutely could just spend the rest of the time going over expressions too. At least maybe like get a start to quasi quotation, because that's going to take, I'm thinking, multiple.
Yeah, I mean, I haven't read it yet, so I don't know, but if
Yeah.
this chapter is any comparison.
I think it's going to be
Quoting,
longer.
unquoting, yeah.
I kind of read it a little bit. I'm a little bit ahead, but I obviously slowed down because I had to put these together. I think it's longer than expressions, and I think it's more patterns than, well, now that I look at it though, I feel a lot better with these trees now, because when I first read this chapter, I was like, what do these trees mean? I guess maybe we can at least try to get maybe a little bit of this in, just see
Okay.
how far you can get, and then,
No.
because literally
worries.
this is gonna take about half of it, because all I really have to do is just talk about parsing, deparsing, and then talk about these 2 specific cases, and that's not gonna take too long.
Okay, so if we can fit quasi quotation into 1.5, then we'll be back on sync after 2 sessions or whatever I'm saying. We'll be back, but we're not doing half in the middle. That's always kind of awkward, but Yeah,
I
let's
think
do
that'd be
that.
great. Yeah, that'd be perfect. So next week, let's finish up 18. And then if we can get as far as we can in quasi quotation, and then take the next session, we'll be
Wrap it
back
up.
on track. Cool.
Sounds good. This is a tough one, man. Good on you. This is a lot of material.
Yeah, it's a lot of material, but I think a lot of it is just, it's vocabulary. Like, it's just, I think that was the hardest part about this, is like, you're just getting introduced to this new vocabulary of it, like calls, symbols, this. And so a lot of the time it's more spent like rereading it to be like, okay, do I understand what this specific component
No.
is? So.
Totally.
but I think this is going to be important when we get to quasi quotation, because we're going to leverage this knowledge to modify our expressions. And so it definitely is important to know all this stuff. So, but I do appreciate the comment, because this is definitely a stretch.
Yeah. Sure.
Well, any other questions, comments? Anybody else wants to add to metaprogramming or expressions in particular?
No, I gave my,
See you guys next week.
yeah,
See
see
you
you
later.
next week.
See ya.
Here.
Cool.
What's happening with this thing? Okay, yep, see you later. Thanks, man.
Yeah,
Appreciate it.
yeah. We'll talk to you later. We'll see you next week.
Okay, bye.
Have a good one. Bye.